In this video we study a powerful concept in distributed systems, called a shared coin. Before we define what a shared coin is, let's look at a motivating example. Let's say we have a distributed system consisting of several nodes, each with its own input value. In the example here, the input is simply 1 bit. How can the nodes agree on a single bit? We will not look at concrete protocols for this problem in this video. Instead, we keep it generic and just say that the nodes must exchange some messages to learn about the state at the other nodes. If the nodes learn that there is no agreement, they can try to reach a decision using randomness. That is, each node flips a coin locally and sets its value to 0 if the outcome is heads, and it sets the value to 1 otherwise. It is possible that all nodes set their values to the same bit by chance, for example, to 0. Now, reaching agreement is simple because all the nodes have the same value. If we analyze this abstract algorithm, we see that the probability that all nodes randomly choose 0 is exponentially small in the number of nodes. The same is true for the probability that all nodes randomly choose 1. So, if we follow this approach, the expected number of rounds until the nodes all agree is exponential in the number of nodes. Clearly, this is not a feasible approach in practice unless the distributed system is very small. What we'd really like to have is a so-called oracle that returns random unpredictable bits, but it provides the same bit to every node. If we have such an oracle, all nodes will always agree on the coin flip, and so the algorithm will terminate in a constant number of rounds. While this sounds great, there is a big problem. Oracles don't really exist. So the question is, can we get something that comes quite close to an oracle? This is exactly what a shared coin achieves. A shared coin is an abstract random coin that is shared among all nodes. When tossing a shared coin, the probability that all nodes get 0 is constant, and the probability that all nodes get 1 is constant as well. It is important to note that the sum of these two probabilities does not have to be 1, that is, the shared coin toss can fail, but it only fails with a constant probability. Since the probabilities are constant, only a constant number of trials is needed in expectation. In other words, a shared coin is almost as powerful as an oracle. But how can we build a shared coin? Clearly, a shared coin is nothing but another distributed algorithm. Since the coin toss must be random, it is clear that the algorithm involves the use of randomness at the nodes. We will now try to build a shared coin. In our algorithm, each node starts by flipping a biased coin. The probability of getting a 0 is only 1 over n, that is, most coin tosses will likely result in a 1. In the example here, only the node in the lower right got a 0. Our algorithm can handle less than 1/3 of nodes crashing. Unfortunately, exactly the node that got a 0 crashes, but it only crashes after sending off 1 0 coin. All other nodes manage to broadcast their coin values. As we can see, only one of the nodes has a 0 in its coin set after this exchange of messages. In the next step, each node broadcasts the set of coins that they received in the previous step. Then, each node examines all the coins that it received. If there is at least 1 0 coin, the outcome of the shared coin toss is 0, otherwise, it is 1. In the example here, every node got exactly 1 0, and so they get the same result of 0. This is a successful run. But is it really a shared coin as we defined before? Let's analyze the probabilities. Each node waits until it receives exactly n-f coins to build its coin set. After broadcasting the coin set, it waits for exactly n-f coin sets, so each node receives n-f squared coins. Let the set W be all the coins that occur in at least f+1 coin sets. And let's assume that there are at most f coins in this set W. Each node in the set W can occur in at most n-f coin sets, so n-f times the size of the set W is the maximum number of coins that the coins in the set W can contribute to the set of all received coins. On the other hand, by assumption all other coins occur in at most f coin sets, so there are at most an additional f times n minus the size of W coins. Under the assumption that f is less than 1/3 of n, if we sum up these upper bounds on the number of coins in W and the other coins, we find that the total number is smaller than the total number of coins in all coin sets, which is a contradiction. What does this result mean? Since the coins in the set W are in at least f plus 1 coin sets, and each node receives n minus f coin sets, every node receives all coins in the set W. If every node receives all coins in the set W, the probability that the result of the shared coin toss is 0 is at least the probability that there is at least one 0 coin in the set W. Since the size of W is at least f plus 1, which can be about n over 3, the math here shows that the probability to get a 0 is at least around 0.28. The probability that the shared coin toss will result in a 1 is easier, as it is simply the probability that all local coin tosses result in a 1. This probability is about 0.37. It looks like we get 0 and 1 both with a constant probability. So, is this simple algorithm a valid shared coin algorithm? Or do you see a problem with the algorithm? If you want to think about this question a little bit, please pause the video now. We will answer the question when we continue. There is indeed a problem with our algorithm. Let's go back to the first step where the outcomes of the local coin flips are broadcast. In the example, only one node managed to flip a 0. What if all messages of this node are delayed? The other nodes can only wait for n-f messages, as f nodes may have crashed and never send any messages. So, just getting one node to send a 0 is actually not enough if we consider a worst-case scheduling of messages. Or in other words, our simple shared coin algorithm only works if we assume that the delivery of messages is random as well. How long does it take if we assume the worst case? In this case, f plus 1 nodes need to randomly choose 0, and this probability is exponentially small in the number of nodes again. In fact, it takes even longer than the simple algorithm where every node tosses its own coin independently. Note that our simple algorithm fails even without any nodes failing. An unfortunate order of message delivery is enough to derail our algorithm. Let's summarize what we've learned in this video. We introduced the powerful notion of a shared coin. We then attempted to construct a simple shared coin algorithm based on the result of local coin flips. We found that the algorithm actually works well, but only under the assumption that message delivery is random. If we consider a worst-case order of message delivery, we found that the algorithm doesn't work well at all. In the standard asynchronous communication model where we consider the worst case, we need different techniques to implement a shared coin. Thanks for watching.